everyone, thank you for joining us and be welcome to our webinar today, Root Cause of PID Control Issues, Identify, Isolate, and Resolve with Confidence. My name is Vera. I'm from Control Station. I work in the marketing department and I will be hosting this webinar with Bob and Lindsay today. And before we start, I just want for you all to be free to input your questions and comments. Anytime you want during the webinar, there is a tab in the control panel named questions. So just tap your question. And in the end of the webinar, Lindsay and Bob will be answering this question. Our presenters today is Dr. Bob Rice and Lindsay Wilcox. So Bob has over 20 years of engineering and product management experience in the process industries. As a recognized thought leader, Bob oversees development of Control Station's award-winning suite of process diagnostic and optimization technologies, including Plant ESP control loop performance monitoring solution. And Lindsay is a customer success manager at SICK, where she partners with global process manufacturing companies to accelerate analytics adoptions and deliver business value through advanced data insight. With over 15 years of experience in industry and software across multiple process industry verticals, she brings a strong background in process control technology. For those who are new to Control Station, we've been driving innovation in process control since the 80s. And today we are proud to support customers all around the world, including many of the leading manufacturers across the process industries. And SICK are a leader in industrial analytics, helping organizations across globe turn raw process data into powerful insights. With advanced analytics, AI, and monitoring capabilities, SICK accelerates digital transformation and drives measurable improvements in operational performance.
Excellent. So thanks for that introduction, Vera. Let me go a little bit over the agenda and the topics that me and Lindsay are going to cover today. We're going to talk primarily around kind of the troubleshooting and root cause analysis on PID control performance and some of the different techniques and challenges and process that you can use to do the troubleshooting and so forth. And we'll go through a little bit of a case study, and we're just kind of draw on our experience and kind of talk through different ideas and different techniques that we've both used to do troubleshooting for PID control. We're going to start with going through the importance of PID control, covering symptoms and poor performance, going through kind of the analysis process. What are the different methods and tools that we can use to uncover those issues and things we can do to streamline it, and talk about forensic analysis and so forth. Followed up by obviously the case study, and then we'll take any questions and answers. So if you have questions, Vera mentioned earlier, there's a little tab that you can go and type in your question. We'll try to get through as many of those as we can today, but any that we don't get to today, we will actually respond to via email following the webinar. So Vera, if you'd go ahead and flip to the first survey question here.
Sure.
What we want to do is kind of go through a quick survey to get everybody's thoughts and opinions around how do you currently identify root cause performance, right? What is your process? Do you rely on internal or external experts using corporate process automation experts? Do you have software tools? Did you build a process? You just got the gut feeling or instinct because you've worked at your facility for a long time. I mean, there's kind of a lot of different approaches there. You know, Lindsay, in your kind of experience over the last 15, 20 years, where do you typically see companies? How do they do root cause analysis?
Yeah, so ideally, we would have software tools that are applied and monitoring key parameters against limits that are benchmarked. I would say in reality, that's not always the case in reality. I think we see, it's not uncommon to see a lot of companies relying on that gut feeling, or maybe not quite having a process, or kind of waiting until there's a more significant failure that shows up in other ways. And obviously, you know, these software tools can be leveraged to help move folks towards more of a continuous improvement type method. How about you and your experience, Bob?
That, you know, that aligns perfectly. Is you've got you basically almost have status quo. That's the way they've always done it. They've got, you know, 20 years experience or 10 years experience. They just use their instinct, or they wait for something to completely fail and then they go and do the analysis. You know, software tools obviously make the process significantly easier. It becomes much more structured. It becomes much more repeatable. And so you can derive that continuous improvement if you've got the tools, but you got to have the tools, you got to have the process, you got to have that kind of internal synergy with, you know, corporate teams and engineering teams to drive the use of the tools. Vera, how are we doing on the results?
Yeah, I'm going to share the results now.
Brilliant. All right, so look at that. Rely on internal and external experts or gut feeling and instincts. How's that for a surprise? It doesn't surprise me at all, right, Lindsay?
No, not at all. And I think it's important to remember too that those subject matter experts are so critical. We're never going to replace them, but I think modern tools can help accelerate their work and also make sure that they're spending their time on the highest value add activities.
Absolutely. I mean, I'd love to have a ton of SME subject matter experts at all the facilities doing all the analysis and the work, but they're becoming fewer and far between. And you know, that instincts and that gut feelings, unfortunately, will retire with them as well. And you know, then I think what you end up with is that 50-60% of results are going to end up into that bucket that says we don't have a process, right?
Right.
Unless they go to looking at tools. That's great. So if we kind of talk a little bit about the importance of controller performance, right? Everybody here kind of understands intrinsically how important the performance of a control loop is and how your plant performance starts with healthy PIDs. You know, the reality is there are a lot of opportunities at plants. There is no perfectly performing plant. I mean, it may be that way for day one and day two, things will start to change. There's always opportunity for improvement. I don't think I've ever gone into a facility and said, oh, you guys are perfect, excellent, we don't need anything at all, we're moving on. There's always that opportunity. In fact, some of the surveys we've run show something like 15 to 20% of all control loops aren't even operating in the correct mode. So that's already 15% of assets that can be optimized, right? So, you know, if you go through and do this effort, where do you see the return? Where do you see the kind of financial value? And, you know, these are typical, right? You get increased throughput, 2 to 5%, improve the production yield, decrease defects, decrease energy consumption. I did a project, I was probably like 10 years ago at a refinery. We just did optimization on all the utility loops. So anything that used cooling or anything that used steam, we went through and tuned all the heat exchangers. Whatever the variance that we removed, right? We may have removed 1 or 2 degrees, then we moved the set point up 1 or 2 degrees, right? And we just kind of use that as kind of a minor bit of improvement in variance, move the set points, and we were able to decrease energy on those loops by 1 to 2% pretty much consistently. Very little effort, fairly high return. So the dollars are there. They tend to be a little bit tricky if you try to look at it from an entire facility standpoint, but if you tend to focus in, the opportunity is there. You know, Lindsay, you know, what are some of the values that you've seen with doing just plant optimization in general? Do these type of statistics align with what you've seen in the past?
Yes, absolutely. And I think the PID controller really is so important because it's on the front lines, right? It's kind of that frontline decision maker. It's in every process, every vertical, whether it's chemicals, oil and gas, pharmaceuticals. It's making those split-second adjustments in the process to control temperature, flow, pressure, whatever that process variable is. And as you said, with your example, when everything's well tuned and operating well, we're happy, the process is smooth. But on the flip side, when we have poor tuning or interactions, oscillation, poor strategy, the whole process can suffer, and we see those issues kind of cascade throughout.
Absolutely.
So if you want to go to the next slide, Vera. So from my experience working, like I said, with manufacturers kind of across process verticals, when there's an issue, we don't necessarily start with the PID controller, right? You're generally, that problem or that issue in operation generally shows up at a higher level. There might be something like a dip in production rate or a spike in energy consumption, or an off-spec batch. And so when the issue comes up, engineers aren't necessarily investigating a PID or a control issue. They're just reacting to a process level symptom. In cases like this, it can be really valuable to leverage modern technology to help quickly contextualize data, kind of narrow in on when the event actually occurred, dive deeper, see what led up to that event. And in some cases, it often does lead back to that underperforming controller that we talked about on the previous slide.
Yeah, I mean, it's those PID controllers, again, they tend to really be the kind of heart and soul of everything. And so when things start to oscillate, you get a lot of operator interventions, a lot of kind of focus on it. You've got the problems. What are some causes of poor control, right? And there's probably 10 times as many that's on the screen right here, but we can only fit so many on a slide, right? When you're talking about poor controller performance, everything can impact it, right? You could be changing rates, you could be changing products, you could be changing grades, you could have an operator come in and decide they want to run the process in a completely different manner, right? You could have poor sizing and turn down of valves. You could have control strategy design, right? You could actually have a PID loop programmed in the PLC or the DCS not to standard, not to code, right? Maybe you don't have you've got override control, and the wind up in that controller is actually causing the output to lock in one direction or another and not recover very well. It could be poor tuning, it could be valve issues, nonlinearity. I mean, the list is endless, right? And so when you're talking about trying to diagnose and understand what's going on with a control loop, you really have to kind of look at the data, look at the metrics, and have tools to help decipher it, right? Be able to put context to it, right? Hey, we have an issue. When did that issue occur? What are the causal reasons for the issues that are happening? Oh, it's these PID loops out of 100, right? And yes, if you've been at the plant for 30 years and you've got all of that gut instinct, you may know, yeah, it's this area right here. But if you've just started, or you've got only 5 years experience and you've never worked in that area of the plant, you're just staring at trends, right? You're stacking traces and just hoping something pops out of you, like that kind of magic poster at the old malls in the 80s. Okay, I'm showing my age, but you can stare at it and hopefully eventually something will come out of it, right? And that time is just, we don't have that time to be able to do that type of kind of root cause analysis. And so you really have to isolate what the issue is. You have to uncover where the problem is and try to do that. So Lindsay, when we talk about analysis and isolation of these issues, what are some of the different approaches or techniques that you would use to maybe identify, isolate, and resolve these?
Yeah, so I think it's all about contextualization, being able to, and we'll talk about this in a little bit, but there's just so much data that's out there, and not just in the plant historian, but from multiple different data sources, whether that's MES, batch systems, lab data. There's just so much, and be expecting an engineer, even a subject matter expert, to sift through all of those trends over weeks and weeks or years and years of data is just unrealistic. Also, not a very valuable use of their time. And so having tools that can kind of quickly and easily zero in to user-defined time periods of interest can just really help accelerate that. On the flip side, we are never going to replace the subject matter expert. And I think having the tools to really accelerate that investigation by adding the context, being able to do things like isolate time periods of interest, test hypotheses, overlay trends and tags, can just help them be able to gain insights and identify root causes quicker and faster. So I'll go to the next slide. Yep, thank you. So the whole process of root cause analysis is so much more than just identifying an issue. It's everything that Bob and I have been talking about, from investigating, resolving, and then of course communicating. Root cause analysis in most investigation or in most organizations extends just beyond that engineer that's doing the analysis, right? That's kind of the tip of the iceberg, is just, you know, identifying the issue and then the engineer doing the work. But there's so much more that needs to be documented and communicated. You know, just as some examples, operations need to know what happened and why so they can prevent it from happening again. Maintenance wants to know what to fix. Leadership, of course, wants to know the risk and impact. And unfortunately, and I've seen this in my experience, and I would assume Bob would agree, that too often the root cause analysis is living in screenshots, emails, or worst case, you know, someone's memory. And so not only can these modern tools and applications help accelerate the work and the investigation, but it's also that documentation piece and the quantification of results. That's going to be ultimately what helps organizations move from firefighting, which is what we often see, to that actual true knowledge capture and continuous improvement.
Yeah, and I'll add to this, you know, tools for doing root cause analysis and isolation. The key is it kind of lowers that cost of curiosity. When you want to go and do an evaluation of things, you could spend days pouring through trends and doing all of this. And that's unfortunately days that you probably should have been doing something else, right? Tools can really kind of be that force multiplier to be able to get to the issue. And then at the end of it, you've got the documentation of how you got there that now you can share with others, you can save it, you can share it, you know, and that becomes a living tomb of how this information was done in the first time. So a year from now, 6 months from now, whatever it is, you can go back and say, okay, this is what we did before. Let's repeat that exercise. And so you're starting to store this information. So often that kind of troubleshooting knowledge, that interaction analysis, root cause analysis, it lives in somebody's mind or in their notebook that they walk out with when they retire, right? Or it's in a notebook that nobody knows. I'm sure we all have. I know I have stacks of notebooks. I'm sure I have brilliant notes in it. I don't know where that is anymore, right? And so being able to store it and retrieve it and share it and communicate it is a really, really important aspect of this. If we want to go to the next slide here, and we'll do a little bit of a survey question. You know, and it really comes down to how do you respond now to controller performance issues, right? We've got a controller issue. What happens, right? Do we just ignore them? Right? Because hey, eventually they'll cause enough problem that you can't ignore them anymore. That you actually troubleshoot the loops yourself. So you go out and try to figure it out. You call for help, or you just put it in manual and, you know, hope it passes. Right? You know, what's your process? What do you do now? Right? Hopefully you're troubleshooting the loops yourselves, but you may not have that expertise. Right? You know, Lindsay, when you would go into plants or you talk to staff, you know, what is the troubleshooting process at sites that you see now? Does it tend to be more internal or external? You know, what's some of the examples there?
Yeah, I would, maybe surprising, maybe not surprising. I would say I frequently would see operators putting troublesome loops in manual mode. Obviously not what we would realistically want them to do, but you know, when they don't maybe have the expertise or the tools to kind of dive deeper, that would be kind of a common way of just addressing what they perceive as the issue. You know, potentially kind of escalating it to the controls personnel. I would say when we did see operators go in and try to troubleshoot underperforming loops, it was kind of a little bit more of trial and error, trying a different tuning parameters, seeing if it worked, and so on. Not a lot of kind of in-depth analysis, I would say. How about you, Bob?
Yeah, I mean, it's the sad reality is most just put in manual and sometimes don't even tell anyone, right? And one of the interesting metrics that we tend to track are things like operator interventions. How many times they're putting it in manual or making adjustments to the outputs while in manual, or set points to try to bring the process under control. And that just shows a lack of faith in the controller being able to do its job, right? You think of the scenario of there's a big upset condition coming your way. The operator has no faith in the controller. They now have to stop what they're doing, put the controller in manual, move the output where they want, put all of their attention on that one PID loop when there could be hundreds of other ones that need their attention, right? And it's just they don't have the faith in that control to do its job, and that's part of their job, and they may not be communicating that out as much as they should be.
Right.
Vera, is there? Yeah.
Yeah.
Look at that. Put it in manual.
Yep.
Almost like we know what we're talking about, isn't it, Lynn?
Yep.
Right. That is the reality, right? It doesn't work. Put it in manual. Hopefully, somebody put it a turnaround log or something that, you know, the next shift comes in, the shift change log to say, hey, we put this in manual. You should probably look at it. But sometimes it's just in manual, and someone will find it eventually, right? So.
All right, so when we talk about root cause analysis, there's obviously challenges or some things that can make it difficult. And we talked about this a little bit already, but there's a lot of data out there. So the challenge isn't necessarily a lack of data, it's actually the opposite. Every site, every plant that I've been to, regardless of industry vertical, has a data historian. Sometimes they have multiple data historians. They might have a local historian, a global historian, lab systems, MES systems, batch records, maintenance logs. So there's just so much data out there, and it's often stored in disparate locations, different vendors. There's not an easy way to pull that data together manually. And so when something goes wrong, though, we still expect that process engineer or engineer at the plant to be able to spot the issue by eye and just immediately kind of zero in on what's been happening. That's not realistic. And so we need these modern applications to be able to line that data in a single location. And we've talked a little bit about contextualization. So what do we mean by contextualization? That's really the way that the engineer or the subject matter expert can just kind of quickly and easily define the time periods that they care about. And there's different ways that they could define that time period. It could be things like, show me when my throughput dropped by 5%, or show me when my valve is oscillating. Show me when my energy costs spiked. So there's all sorts of different ways we can use logic to define those time periods of interest. And that will help ultimately engineers move from hunting and guessing to more structured investigation, and allowing those rules to kind of scrub their data for them so that they're already starting kind of with those time periods that they can really zero in on. What's your experience been with this, Bob?
Yeah, I mean, I think that you're spot on. If all you have is process data, you have raw process variables, outputs, set points, modes, you've just got the raw data, you're not getting the context to the data, and you're not actually getting what's actually going on, right? You have to have other tools kind of interpret the data to say, hey, is this loop oscillating? Is it not? Does it have tuning issues? And then say, okay, show me, you know, things that are oscillating around this time, right? And be able to kind of put context to what's going on and capsule define, hey, this is the event. You know, there was an event that happened here. Show me all the things that were going on at that time that may contribute to it. That is the troubleshooting process, right? And sure, could you do that manually? Yes, with lots and lots of trends and lots of time, of which I'm sure we all have an abundance of at this point, right? So having tools to be able to kind of sort through this, provide context, organize it, and document it in a way that makes it a lot easier, just makes that troubleshooting process so much easier to do, right? We have an abundance of data, right? We have massive amounts of data. And again, as Lindsay said, one of the challenges is not all in the same spot, right? It's in lots of different sources. So being able to pull it together into a single source and kind of give you, almost like single source of truth, right? I only have to look in one spot to find my answer. I don't have to go find the 50 spots. Really makes that kind of analysis and root cause a lot easier. And so now what we want to do is talk a little bit about the methods for doing this root cause. And again, we've only got a short amount of time in this webinar. I could probably spend hours on these next two slides alone, but I'll do my best. So Vera, can we pop over to the next one? So when we think about adding context to data, right? When we're talking about saying, look, I've got raw process data, can't I just look at the process data and tell you what's going on? Sure, if you've got a trained eye, you've been doing this for a while, you can probably look at an oscillation on a flow loop and say, yeah, that's probably got valve stiction, or no, that's a tuning issue, or no, that output's saturated. But there are a ton of KPIs that are designed to put context to that performance, right? To say, hey, look, this is a tuning issue, this is mechanical, this is a saturated valve, this is a oscillating loop, this is a sticky valve, this is a loop with high variance versus low variance, right? You're putting kind of more information to what's going on at that point. And that's really what KPIs are about with controller performance, or any process in general, is you're taking the raw data and you're actually turning it into something that is useful. I mean, think about driving your car, right? Yes, if you're a car nut, you can look at your oil pressure and oil temperature and all those things and tell you when you have an oil problem, but it's a lot easier if there's just a light that flashes that says, hey, it's bad, go look at it, right? That's what, you know, most people need, right? And that's what the KPIs are really about, is to take all of the raw data and actually turn it into kind of useful information that now can be flagged and used to run analysis on that, to say, hey, show me everything when, you know, oscillation was high, or when valves were high, or show me all the oscillating loops within this time window, whatever it is, right? You're taking the context and putting it to the data, so you're not just looking at raw trends, because that's just time consuming, right? And so when we think about trying to do that type of analysis, it's trying to organize that information into kind of a troubleshooting process. You know, Lindsay, from your standpoint, when you're, you know, doing troubleshooting, what are some of the steps that you would use for kind of building out a report or building out a process, and the methods that you would use for that?
Yeah, I think knowing the KPIs that are important for your process is really the starting point, but it's more than just being able to calculate the KPIs. It's you referred to the meter in your car. It's being able to know what's a good value, what's a bad value, having limits on those KPIs, and being able to flag whether that's, you know, an email or a report that says, hey, there's something that's starting to deviate in this KPI for your process. I think that's kind of when you're able to take it from responding to issues to being able to kind of catch them in near real time and being able to respond to them to make improvements to the process. So if we go to the next slide, there are some great tools or methods out there that can be used to help identify interactions. And so when we think about interactions, it's important to remember that those are all the subtle ways that our process is interrelated. So often when our loops or our variables in our process are failing or in a poor state, they're not there alone, right? They're impacting processes or control loops that are upstream and downstream. And so how do we get to the bottom of those interactions? So the screenshots you see on the slide, those are a type of frequency analysis or power spectrum, where we can identify what those common frequencies are in our signals. And so you know, if a loop or a process variable has let's say a 30-minute oscillation in it that's shared with other loops in the process, there's a pretty good chance that those loops are interacting, right? There's other methods we can use to identify interactions within our control loops as well. One example that comes to mind as well is leveraging modeling, so building a model of our process signals and then evaluating our squared values to see how related or kind of what the relationship is between those loops. And that these are just some examples of different methods that we've used or deployed to identify kind of those relationships between our control loops and process variables.
Yeah, and the, you know, trying to find those relationships is really the key point of troubleshooting just in general, because oftentimes the control loop that's actually maybe the operator flagged as being a problem isn't necessarily the source of it. You have to identify where is that variability actually coming from. It could be a temperature loop here that the operator flagged because that's critical, but it could be because, hey, this pump is cavitating 3 units up and causing swings and oscillations. And so being able to identify those kind of shared swings, those shared oscillations, is really important. One of the things I really like about power spectrum as kind of a weeding approach to kind of weed out all the noise in a system is it doesn't care about the phase shift between the oscillations themselves. So you could have a 30-minute swing, but it may take 20 minutes before it impacts this one over here. They'll both have a 30-minute swing. They'll just be kind of offset from each other. And so it doesn't care about how long it takes one loop to impact the other. It's just telling you that, hey, these loops kind of shared cycles. It's like a fingerprint, right? If you've got variability that has a certain fingerprint of oscillation, what are all the loops that share that? And you will be surprised. And the thing that I use power spectrum the most for is proving to customers that a poorly performing loop is actually important, because I'm sure everyone's like, oh, I have to go tune this loop. No one cares about it. Well, let me show you, when this thing swings, I've got 10 others that are swinging with it. You care about these. You may not think you care about this one, but you really do. And so power spectrum is a really powerful tool. It works really well. And I can tell you, this is probably the first approach that I use for trying to do root cause analysis, figure out which of the 100 out of the, I only need 10 that actually share together. But what power spectrum does not do is it does not tell us who's leading and who's lagging, right? It's not going to give you any shifts between them very easily. It's just going to tell you that they are kind of shared common frequencies. So if we go to the next slide, this is where you get into the understanding information, the relationship between loops. And again, correlation analysis needs a whole hour by itself. But in short, it's basically a method for measuring similarities between signals, right? One signal changes, another signal will change with it or opposite to it in some time shift, right? Do they move in unison? Do they move opposite? And what is kind of the delay between them? And this is an incredibly useful approach for understanding relationships between signals. And so you can see here, we've got a nice correlation map. You've got all your signals between the X and Y. The square point where they intersect is telling you the measure of correlation, right? Is it heavily positively or negatively correlated? Is there kind of lead or lag between them? And this allows you to start to put things in order. Hey, they're all oscillating, but which one's oscillating first, right? And where's the strength between those oscillations? And correlation is a really interesting tool. You do have to be careful. Causation doesn't mean correlation, and there's lots of stuff around that. But for kind of a directed analysis within kind of a time period where there's something interesting going on, this can give you a ton of information. And Lindsay, do you want to go a little bit more into kind of how you use correlation to do troubleshooting, or what you've done in the past using correlation?
Yeah, absolutely. And I agree with you, Bob. As soon as I know that a control loop is oscillating, the first thing that I want to look at is my power spectrum to know what the frequency is of that oscillation, and then also what else is being impacted or oscillating at that same frequency. Once I kind of can zero in on here are my loops that are oscillating together with the same frequency, then I would take those specific loops into the cross correlation and kind of zero in on that leading lagging relationship. I completely agree with your point about the time lag. When we have loops that are oscillating at the same frequency, but maybe they're offset from each other, it can be kind of difficult to pick up on those shared frequencies without a tool like this. Not only that, but sometimes loops can be oscillating and you might not even know they're oscillating, right? It might just look like signal noise and you might not realize that there's actually kind of a cycle that's actually taking place underneath that noise. And so these applications can definitely help zero in on that. I think you kind of need them both together, right? So it's not just enough to know that, okay, these are the loops that are oscillating with a shared frequency. You then need the cross correlation to be able to say, hey, this one seems to be oscillating first and leading the other two. That can direct you to, that's where I need to start my troubleshooting, whether it's tuning a loop or addressing stiction in a valve. And then once we've seen those improvements, kind of tracking progress going forward to make sure that, okay, we've tuned the loop, are we now seeing the oscillations or the impact kind of smooth out for the rest of the process as well. So if you go to the next slide, Vera, I think that everything we've talked about with root cause analysis and generally what I've seen as well working with customers is that it tends to be localized, right? You have an issue, one engineer investigates that loop or some other unit in the process. It's valuable, right? We want to know what went wrong. We want to document it. We want to correct the issue, but it doesn't necessarily move the needle at a higher level, right? And so the real value from root cause analysis, I think, comes from when you're able to scale that approach to the entire operation. And so that's, I think, where you need these modern applications or software tools to help accelerate that, because one engineer pulling in data into an Excel spreadsheet, doing manual data mining is not a scalable solution. And so you need a repeatable process instead that can be scaled not just from that individual control loop or even unit or even facility, but really more of an enterprise, give the process of the root cause analysis more enterprise level visibility, because leadership's really going to want to know, can they quantify and prioritize control issues, and where are they going to get the most return on their investment as far as prioritizing control strategy type issues. How have you seen root cause analysis be scaled across customers you've worked with, Bob?
A lot of it is that kind of knowledge sharing, right? You'd mentioned, you've got you do a troubleshooting exercise on one machine, one piece of equipment. Well, the enterprise may have 50 of those pieces of equipment. And if you can kind of create a structure or a document on how you troubleshoot at once, right now you've got this that you can now deploy this across different sites. You can also start to standardize performance, standardize metrics, and start to use information from all the different sites to set baselines to raise the performance of everything. What's the best performing equipment? How do you get all the pieces of equipment to that best performing notch? And now you can compare them, and now you can find outliers. It's very easy to uncover controller performance issues when you have a baseline and things to compare it to. If all you have is one thing, how do you know if it's behaving well or not? If you got 20 of them and one's behaving really well, now you've got a really good baseline. You can start to document and build a process that is now repeatable, right? We all have lots of systems that are the same across, and we know our best performers and we know our worst performers. Well, how do we get those up? And so the root cause analysis, being able to just knowledge share, is a huge thing, and to document that process is huge. And so when we talk about kind of the root cause, one of the things we always have to do is try to end up with a tuning process at the end of it. And if we go to the next slide here, this will be a little ad for our next webinar that we're doing with Helen at Rotico, and Damien, one of our engineers here, or head of partners now, talking about PID tuning with dynamic process data, right? When we are going out and tuning loops, we always don't have the perfect bump test that you see in textbooks, right? We always have imperfect data, oscillations, swinging, noise. And so Helen and Damien are kind of go through the process for analyzing data that is less than ideal, right? That doesn't look like it comes from a textbook. So if you want a good webinar on how to kind of tune loops with bad data, next month, Helen and Damien are going to do a good job kind of going into the background and the process around that. So we'll go ahead and do, we've got a little bit of time left here for our case study. This was a project done a number of years ago. It was a combined cycle gas-fired natural power facility. And one of the primary things that this customer was concerned with more than anything was trips, right? And I'm sure that's kind of a common theme, right? You clearly don't want anything to trip, but every single time a turbine tripped, it was between $40,000 and $80,000 in just fees from regulatory compliance. And so one of the things that we were trying to do is determine, well, what was the primary source of these trips? What was the issues that were going on during that time? And you're going to see kind of a common theme here. We talk about the troubleshooting approaches, right? There's variability with these systems, and trying to identify the time at which these variabilities occur, or when the trips occur, and then what is the variability that's happening during those trips, is really what the troubleshooting process was about. And so, Lindsay, when you're looking at working with a customer and they've got a particular issue, what are the approaches that you use that you would kind of set up for them to say, hey, we've got a trip. How do we find the problem? How do we troubleshoot this?
Yeah, I think with this case and any other situation as well, it kind of all starts with defining what good looks like. And this particular case study, I think, is an added level of complexity where we're not looking at steady state, right? We're looking at startup when things are transient, and things are really critical because we're starting up, things have to be moving. So we're not just trying to maintain a base level steady operation. And I think that can become even more challenging because, you know, what's good for a startup right now is not going to be considered good 30 seconds from now or 30 minutes from now, right? Things are constantly changing. And so I think it all comes down to, you know, first step, let's identify those startup events, add the context to the data, of course, characterize what looks good. So let's maybe start by overlaying those good startups, getting a visual representation of, okay, they all kind of have the same shape, right? You can do more interesting things like, you know, building reference profiles of your signal. So what's the overall shape of how I want that signal to look as my startup progresses? And then using that reference to build limits on what a startup should look like as good. So knowing what good looks like, I think will help to identify deviations or drifts as the startup progresses so that you can see them and respond to them in near real time. So hopefully you're able to avoid that trip from occurring in the first place. And if we go to the next slide, we've talked a lot about oscillations, and I think oscillations become even more critical when we talk about startup, right? So oscillations like that that bright green signal we see on the screen, you know, when things are stable in a process, at worst, your oscillations can be wasteful. They add wear and tear on your mechanical components like your valve. But when things are transient, like during a startup, it's not just wasteful. It's so much more than that. It has the opportunity to be really detrimental to your process and potentially cause that turbine trip that we've been talking about. Obviously, in this trend, we're seeing the oscillations are super obvious. I wouldn't need any sort of software to tell me that there's an oscillation happening here. That's not always the case. Signals have noise. There's the potential for the oscillation to be kind of masked by the noise we're seeing in the process. And so the first step really is identifying that you have an oscillation. And that all starts with kind of the subject matter expert knowing I want my loops to be operating stably, especially during startup, monitoring that oscillation KPI to be able to quickly and easily identify that things are starting to kind of cycle at a repeatable frequency. Mm-hmm. What is your experience with
yeah, this? Oscillation is one of those things it's equated to instability. When things are oscillating, there's the opportunity for things to become unstable. And if we go to the next slide, right, with this particular example, we were able to isolate a particular drum that had a fairly consistent level of oscillation. Sometimes it was in the green, but most of the times it was up in the yellow and the red, right? So there were lots of startups and shut down. This was kind of a machine that a system would come up and down all the time. And there was a fairly strong likelihood of consistent oscillation, right? And this was an IP drum level, right? And so the question is, well, who cares, right? Okay, we can probably fix the drum level, and is that really going to be the source of our problem? And so this is the identification of the problem, right? This is, hey, here's a loop that's swinging. Let's see, is there a way that we can determine if this is actually causing our problem? And this comes down to the methods that we talked about earlier, doing kind of spectral analysis and correlation analysis. But the analysis that we did on this drum level, we showed a very strong reoccurring 50-minute cycle, and we believed that it actually had a significant impact on the gas performance heater and boiler level, the primary boiler level of the system. And so maintaining tighter control, more stable control should be essential for trip avoidance. But is that just, me making something up, or is there data to actually back this up? And so, Lindsay, I'm sure you want to pop over to the next slide and kind of talk through the.
Yeah, so we know the loop is oscillating. We see that in the data. So the next thing I want to know, like Bob said, is what's the frequency of that oscillation? What other loops are oscillating with it? And what's the lagging relationship between the loops so that I can really zero in on where I need to start troubleshooting or kind of making tweaks, or whether that's tuning or any other corrective actions that I can take. And so frequency analysis and cross correlation we talked about quite a bit, but as Bob said, it's really about being able to leverage the data and the tools to be able to back up any sort of conclusion that you can come to make the justification for any process level changes that are made, that we really have clear evidence to back up our conclusions.
Yeah, and it's really about that evidence, right? Because anytime you ask for somebody to make a change, especially to a boiler system or a critical asset, they're going to want proof that this is the thing that needs to be fixed, right? Just saying, hey, this is broke, go fix it. We need proof, trust but verify, right? And so we often use kind of forensic analysis. Say, yeah, here is a loop that's oscillating. Look, it is actually driving the variability towards these two other loops. And, to kind of just, wrap this one up, if we flip to the next slide here, this was a tuning issue. We were able to go through, identify the loop, do a bump test, generate tunings, remove the oscillation and the instability through a simple tuning exercise. Those are the easiest and greatest wins, right? Tuning is easy, right? If this was a mechanical issue or a valve issue, we're gonna have to write a work order and hope that it gets corrected sometime in the next 6 months, right? But oftentimes you can, identify oscillations, and if they are tuning, let's go fix them, right? Let's go try to apply some corrective actions and try to make some improvements here. And here we were able to reduce the overshoot and oscillation here.
Yeah, and I think
yeah.
the interesting thing too, or what's always a good idea, is to be able to track any changes that you make going forward. So you apply those new tuning parameters, then what happens, right? Are we seeing those oscillations go away? Let's quantify the impact of those changes. Leadership always loves to see the impact on the equipment or the raw materials that are being used, and ultimately the over quantifying the positive results to the process.
Absolutely.
So if we go to, I believe it might be the last slide. So to wrap up, there are a few key takeaways from today's session. Hopefully this was informative and educational for all of you that are listening. But first, I think the PID performance is really important. It's like we talked about, that frontline decision maker making those split-second decisions that directly impact plant safety, efficiency, profitability. So it's not just a control issue, right? This impacts the business. Second, it's important to distinguish between symptoms and causes, being able to know what parts of my system are interacting and what's leading and lagging, so that you can really zero in on where you should spend your troubleshooting issues. It's important to have a structured approach to your root cause analysis, so that it's not only repeatable, but also documented, easily explained, with quantified results that you can share with your colleagues or the broader organization. And finally, it's easy to get overwhelmed by all the available data that's out there. But I think having the right tools that can accelerate that subject matter expert and knowing where to start makes that task so much more manageable, but also repeatable.
Yeah, and I think that takes us to our kind of final bit of survey, and then we'll do some Q&A here. If you need any information on any of these topics, please let us know, and we're happy to share it out.
Yeah, here you can check all that apply. So we have, if you want more information about PID performance monitoring, benchmarking tools, control loop, audit and process optimizations, the calendar of the PID training, the schedule of the webinars, or to download the OC white papers, just let us know. And then we will go to our key questions. So again, feel free to input your questions in the panel here. Okay, let's start with the questions, Bob and Lindsay. Beyond traditional tools like power spectrums and correlation analysis, how are you applying AI to facilitate root cause analysis?
Okay. Lindsay, you want to start with that one?
Sure. Yeah, so AI, I think, has become so embedded into the way that we function, not just at work, but in so many different parts of our life. And I think that data analytics or root cause analysis is no different. So within Seek, for example, we have several AI assistants kind of throughout the platform to help with things like writing Python code or just leveraging different applications within Seek. And so the AI assistant is really, I view it as kind of an accelerator for things like, you could open your AI assistant and ask questions like, I'm doing a root cause analysis on this loop and I want to know what it's interacting with. What tools or approach would you recommend? So it's kind of that overall approach or process that it can help with. It can recommend formulas. It can even take things a step further and actually execute actions for you as well. And then another thing that I always like to note, and it's maybe not the flashiest capability, but it's very important, and that's the documentation piece. The AI assistant can basically take that analysis that the engineer built and just automatically document all of the steps that were performed. Again, taking the engineer's time, not spending it on documentation and reserving it for kind of higher value add activities.
Yeah, so one of the interesting things too that we've been experimenting with here is on the kind of the causal AI side, using things like gradient boost methods for doing causal analysis between variables, right? And you could think of it as like correlation analysis on steroids, right? Where you can maybe give a hierarchical structure to, control loops, tags, systems, variables, whatever it is, and start to say, okay, well, I've got all of this process controller performance data. I've got 1 or 2 or 3 business KPIs, production KPIs. Can I start to understand relationships to build kind of these predictive models between the KPI data, not raw process data, but KPI data and business KPI data? How do you build those relationships and those causal models? I think there's a lot of opportunity there. We've been doing some research projects with the University of Connecticut to kind of push that even a little bit further. I think it's really exciting, but AI is the latest buzzword, so you do have to be a little bit careful with some of it, right? But there is some really neat stuff that's coming out there, and I love being able to use the AI assistant to document, because I can tell you documentation is my least favorite thing about anything. So having the tools to be able to automatically document it is brilliant.
Thank you. Another question here. Does the tuning require try and error till you get the right values for the PID, or you probably use AI to enhance the tuning?
Tuning from our side is done with a model-based method. We take process data, step test data, bump test data, analyze it, and generate models to calculate tunings. So it is a model-based approach to be able to do that. We don't really recommend trial and error tuning if you can avoid it. Model-based tuning is far more documented and repeatable than trial and error. And so we have model-based tools for generating tuning parameters.
Thank you. AISA 95 talks about enterprise automation system architecture. Has control station been involved in AISA 95?
So with ISA 95, that's basically kind of the data structure behind everything, right? So you've got the enterprise model for kind of the levels and the framework. When we set up things for loop monitoring and for kind of setting up a kind of an enterprise monitoring system, we try to follow the tenets that are in there as far as how the enterprise is structured and the different components attached to it. So it's just a kind of a reference to how things are structured. Additionally, we are very keen on data interoperability. And so all of our process data, all of our analytics, everything that comes out of our tool can be natively consumed with REST endpoints to be brought into other tools. And so especially tools like Seek that add a lot of context, bring data in from different systems, it can pull data right in from ESP and start adding context to all the other and analysis between all the different systems applied to it. So from an interoperability standpoint, 100% in, right? That is, you can't have a single silo of data that you can only use it in that one tool. Everybody wants to use it in every other tool. And so having that interoperability is absolutely key to being able to use data more freely.
Thank you, Bob. What are interface options for control station with existing controller, either PLC based or DCS?
So with our tools, we support all the open communications, OPC, HDA. We've got data historian connectors for all the modern data historians out there. We can connect, OPC UA, OPC DA, OPC HDA, all the, kind of all the open standards that are out there. If you've got data in SQL or ODBC or OLEDB, we can connect to those as well. We use all the kind of open different interfaces. And I imagine, Lindsay, with Seek, it's kind of a similar breadth of kind of open interfaces that are available to you guys?
Yeah, so we connect to wherever your data is being stored. So there does need to be a data storage location. But absolutely, Bob, we have standard connectors to pretty much, the wide breadth of historians that are on the market.
Perfect. And if we company, we both use Seek and PlentySP, how should we leverage them for the greatest benefit?
So that's a great question, and honestly, why we're on this webinar together with Seek, right? I think PlentySP does a really good job of giving you controller performance KPI data. Seek is really good at taking data from all the different sources and being able to provide context and identify it and work together. And so bringing in ESP as a data source, as an interface into Seek is the ultimate goal. We're actually finalizing our interface for Seek now to be able to actually natively consume ESP data in the Seek interface.
That's great. And the last one, what different source of data is needed to perform this type of analysis?
As far as sources and quality, I mean, you need good quality data as far as if you're doing interaction analysis, frequency analysis, correlation analysis, you can't have 60-second data, right? You're going to need kind of higher resolution data to do things like frequency analysis. If you have 60-second data, you're at best going to find, 30 to 50-minute oscillations. You're not going to find anything that's high frequency. And so you need data channels that are free of sufficient, that are not aliased, that aren't highly compressed, good quality data. We've got some guidelines on recommendations on, exception and compression and what data channels are there, but you generally need process variable output set point modes, and you need them sampled at a rate that actually makes sense, right? Not 5-minute data, not 60-second data. And I know that can be difficult, right? Sometimes getting faster than 1-minute data on a DCS that's 30 years old can be problematic. So,
sorry, Bob, there is 2 more actually. So, how do you select the signals to be added in the power spectrum analysis? Manually by experience, or there is a smarter data-based way?
For power spectrum, I tend to find a loop of interest that has a high likelihood of oscillation, and then within ESP, you can just click a button and it'll show you all the loops that kind of share that frequency. So you start with one that's of interest, that's got cycling, and then you can say, run the analysis against all the loops in a system, and it'll rank them at the top and say, hey, these 20, these 10, these 15 have strong shared frequencies, and then you can kind of focus your analysis on a subset of loops. So there are some tools to kind of run the analysis on everything and say, out of those, hey, only these 10 have whatever, strong likelihoods of oscillation attached to it.
Perfect. And how often to identify the PID tuning from your model simulation, yearly or monthly after finishing first job?
That comes down to is how often do you think the process changes, right? How often do conditions in the process change? And that could be monthly, weekly, yearly, decadely, right? It really just depends. So anytime the dynamics of a process change, the tunings could change. And so you just have to kind of understand how much do the process conditions change. anytime there's a major update or upgrade to the process, right, that's usually a good time to do some tuning. But it can be more frequently than you like, especially if you're changing product grades, product lines, rates, stuff like that. It can be a lot faster. And so it just depends on how much your process changes by. That's my pocketbook answer, is it depends. So
yeah. So we are actually running out of time. We have three more questions here, but we will send the response by email. One of our specialists that is in your screen will be in touch with you with the answers. And if you have any questions, any comment about the webinar, feel free to let us know through our website. And thank you all for joining us. And don't forget that next month we will have another great webinar with Rotico as partner. PID tuning for dynamic process, even with imperfect data. So have a great day, great week, and thank you all for joining us today.
thank you, Vera. Bye, Lindsay.
Thank you.
Bye, Bob. Bye, Lindsay.